Conservative gradient forces usually hold microobjects in one place, for example, inside optical traps. Non-conservative forces, however, can manipulate objects over long distances. One peculiar case of non-conservative forces is the negative force, also known as a tractor beam. This force acts in a direction opposite to the overall energy flow. Negative forces usually appear if the momentum of light increases in the process of scattering. As it was shown in this recent paper, negative forces can appear for objects placed at the surface of liquid dielectric media. The amplification of linear momentum happens because the momentum of a photon is proportional to the refractive index of the medium. This momentum amplification creates a reaction force that drags the object in a direction opposite to the beam propagation. The approach proposed in that paper works for an object half submerged into the liquid substrate and does not work for solid interfaces when the particle needs to be completely outside. The question is, can one create negative forces for solid interfaces? The proposed solution is based on surface waves, namely surface plasmon polaritons. These waves exist on metallic interfaces when the dielectric permittivity of the substrate is negative. The wave number of surface plasmon polaritons is larger than that in vacuum. Thus, if we convert scattered light into surface plasmon polariton waves, we can increase the optical momentum. Here is the overall concept of the approach. The interference of the incident and reflected waves creates a rotating dipole with an asymmetric scattering pattern. The rotating dipole excites unidirectional surface plasmon polariton waves. Surface plasmon polaritons carry away large linear momentum. As a result of momentum conservation, the reaction force moves the particle in a direction opposite to the surface plasmon's propagation. For a dipole-sized object, the proposed concept can be described analytically. For a dipole near a semi-infinite medium, the local electric field is represented as the sum of the incident field, the reflected field, and the field rescattered back by the substrate. This last term is represented in a framework of Green's functions. The corresponding Green's function was found by a plane wave decomposition of the scattered field. The optical force acting on a dipole can be found using the standard expression. The first term corresponds to ordinary radiation pressure created by the incident and reflected waves. This term is always positive. The second term corresponds to the interaction of the particle with the substrate. This term can become negative in certain cases. In particular, this term can overcome the radiation pressure near the plasmonic resonance. Analytical derivations are confirmed by exact numerical calculations. Calculations were performed using the finite element method. The first figure shows the force along the surface calculated for different wavelengths of the incident wave. As you can see, the force becomes negative exactly in the vicinity of a plasmon resonance. Surface plasmon polaritons are confined to the interface and exponentially decay away from it. This limits the dimensions of manipulated particles. The second figure shows the spectral dependence of the force as a function of the particle's size. You can see that the negative force disappears for particles larger than 30 nanometers. In conclusion, we have demonstrated that an unstructured optical beam can act as a tractor beam along a plasmonic interface. The asymmetric excitation of surface plasmon polaritons induces the amplification of the forward scattering momentum, leading to negative scattering forces pulling objects in the direction opposite to the beam propagation.